Now you can start. Yeah, it's okay for us.
So shall I start?
Yeah, you can start.
Okay, that's okay. So thank you all. Thank you, Omar and Mustafa, and the team for hosting me the IEEE Connecting Experts program on today. So my today's lecture will be on a very interesting topic. Again, I hope that this is also a very interesting in the present pandemic situation all over the world. And so my topic of today's lecture is on the computer-aided diagnosis and how we are using the deep learning techniques to excel in this particular research and activities. And my lecture will be a sort of summary of some of the research activities, and prior to that, I will try to discuss about some of the key concepts related to medical image processing as well as deep learning. So I hope that I am audible to all of you, right? So am I audible to all of you? No?
Yes.
Okay, right? Okay. Okay, so, okay, fine. So as we all know that the concept of computer-aided diagnosis all starts with the medical imaging, and so what it is actually. So medical imaging is something by which we try to get information of the structural elements of our body, maybe from the cellular level to the organ level to the multi-organ level, by capturing the various forms of images, right? And it is obviously pretty complex in the sense that there are multiple ways we can capture the images, and the different forms of images gives the different information of the particular body part or body organ. And also, it is not only the structural imaging, it is also the images can also be generated, which also gives the functional view of the organs. So in a nutshell, this particular domain of medical and we can have images in the different scales and different forms. Some of the common ways of medical imaging or some of the common domains of medical imaging are radiology, like X-ray, tomography like CT or PET. We have endoscopy, we have thermography, and we have also the microscopy images and medical photography. So you can see that though these terms are very that means I have only discussed some of the terms of imaging. There are more imaging forms, and apart from this, each of the imaging forms requires a different types of setup, different type of analysis procedure, and a different types of medical inference we can draw from this type of images. Now, as we have already started, there is a variability in the types of medical imaging and the ways they are captured or the inference they try to generate. Obviously, what we're trying to say is the various modalities in the medical image domain. So as I already told, this is a procedure, a non-invasive procedure. So one good point of medical imaging is that why we go for medical imaging, because first of all, medical imaging is not invasive, and secondly, medical imaging gives a sort of first level of screening before going into actual medical analysis in the level of the tissues or in the level of some of the samples from the body. We can have this medical imaging capture and analysis to give a pretty decent result or pretty decent inference of the condition of the disease condition, and then obviously we can go to the second or third level of investigations. So now I come back to the imaging modalities as I started. So there are various forms of imaging modalities, and these modalities are so varied because each of the modalities have a different kind of interaction with the body organs, and they generate a different types of interpretation of the either the structural, the functional information of those particular organs. So as we see, there are plethora of this type of medical imaging techniques, and I have already spoken a few of them. And similarly, we can also visualize that each of these imaging modalities can cater a particular type of organ or a group of organs, and obviously a group of disease. So as I told, that they can be classified into modalities like tomography, like CT, like X-ray, like magnetic resonance imaging, like ultrasound, and hybrid modalities. So if I just try to tell that what are the differences between the modalities, I can just try to explain you with very few examples. Suppose we are capturing X-ray. So X-ray is nothing but a radioactive energy generated by a radioactive source, and this energy falls on your body, and then there is a plate which captures the energy which has been transmitted through the body. Now normally the hard components of our body, like the bones, they absorb this energy, so the energy cannot transmit through those particular parts of your body which are hard or which are bony, but they can pass easily to the other parts of the body which are soft tissues. So in the image, I will get a different impression or a contrasting impression of the bones and that of the body tissues, and more effectively this particular type of X-ray actually gives you a good information about any deformity in those particular the hard components of your body, or there is any sort of variations in some of the muscular regions like lungs or chest forms. Similarly, CT is also very similar to an X-ray, but in the case of CT, what we try to do, in the case of X-ray, your source of the energy and your detector is static, so you only get a particular region of the body you can scan through the X-ray. When you use a CT, both the detector and the source moves around the body in a 360-degree form, and so you can get a very holistic information, and you can get a three-dimensional information of the body. So what I just now pointed out, once you move from the X-ray to the CT, your modality by itself gives you a three-dimensional information compared to a 2D information when you go to the X-ray. Vis-a-vis when you use a magnetic resonance imaging, what it does, it employs a magnetic field, and the magnetic field interacts with the water molecule, which are the basic components of your soft tissues, and they give a response, and that response can be tracked or can be tomographed to find that whether the response are proper or whether the response are not proper, and that is the most phenomenal way of diagnosing some patches or some disease in the brain, because brain is mostly composed of the, apart from in the external hard skull, the internal of the brain is mostly soft tissue. So you see that once I move from the CT to MRI, the different types of organs I am just trying to understand. And in the case of ultrasound, it is something which some of the organs are very deeply embedded in the body sac, consisting of a lot of fluids. So in this case, a lot of this imaging technique fails due to this fluid sacs which cover up our organs. So ultrasound can give you a good information of those type of organs which are deeply seated in the body. They can understand the depth of this particular this organs, and also using some sort of Doppler techniques. Okay, they can also scan the movement of these organs, whether they are proper or not proper. So what I try to say here is that there's a plethora of medical imaging techniques, and each of the techniques tries to target one type of organ or a group of organs, or tries to find a particular behavior of an organ or a group of organs. So when you look into this entire process of imaging capture and image analysis, what we require is a sort of digital infrastructure, and that digital infrastructure is normally or most commonly used by the medical houses, or very standardized, and that is called a picture archiving and communication system, which involves from the capture to the storage to the display to the special medical practitioners, so that they can visualize the data in the best possible form, and the entire communication network which supports this particular information system. So as you see, that there are components from the capture, storage, and from the visual analysis components which build up this PAC system. With this PAC system, we also have to understand that there are information storage system, very standardized information storage systems in terms of the database of images what we're storing, as well as what are the workflows which has been acted upon on this particular type of images. So radiology information system is a sort of database system where the radiology data, as well as the different types of workflows or the operations which has been done on this type of radiology data, helps the doctors to track the process which has been undergone for a particular patient or for the group of patients in considering radiology images, and that actually helps not only in the storage and analysis of the images, but also to generate a good sort of disease map for a particular individual. And obviously, the entire process of this information flow is based on the image format, which is called the DICOM image format. Okay, and that is pretty standardized, which is used for this entire communication and processing domain of medical images. So this is a sort of workflow which happens in a. Though we feel that a medical house is only for providing medical support, but a present modern medical house to cater the increasing number of patients and to handle the complexity of the diseases, they are really building up a very solid information technology support and infrastructure, and they're using this type of systems for day-to-day operations. So now I come to the very important point of our today's discussion, which is actually computer-aided diagnosis and detection. So though I tell detection though I give diagnosis a more stress, because that is where we are towards. Okay, we are towards an era where we might have the computation in genes or computing in genes will help the doctors to diagnose a disease in a more accurate way. can also help the patients to do an preliminary diagnosis at their point of care, right? And that's why diagnosis is a bit stressed, but obviously diagnosis cannot happen without detection. So first we detect a particular region in a given image sample, that okay, there is something in the region. We put some mark in the particular region. It may be a tuberculosis patch, or it may be a nodule in your lung or brain, and then we try to explore it in a much better way, and try to find out that whether this particular patch, the risk associated with the particular patch. So if I try to define summarize the thing what I try to tell you. So the computer-aided detection is sort of a preliminary screening. It is also called as a radiology-based screening radiology, where we try to this particular figure tells that a particular computer-aided detection, what it tells is that okay, say look, that this is a chest X-ray, and in this chest X-ray I can find a tuberculosis patch which is there, and so my CAD tool, which is also called a CAD-E, my CAD tool actually marks these regions in my image to help the doctors to actually focus or to look into these particular regions to understand the disease at a more fast rate. And this is also required in the many countries, especially if I take the case of India, where we have a large number of population, and we have that means obviously the number of doctors or the medical experts are not scaled up to the level of the population. So many of the doctors are burdened with the number of patients they have to check each day. So this type of early signals, or this type of automated detections helps the doctors to actually utilize their time in a very effective way, and try to give the inference in a very short amount of time. Yeah. So anything you want to say, Omar? Okay, fine. So similarly, if we go to computer-aided diagnosis, actually the figure what I show next, okay, it tells a story. What it actually tells, it tells that once we detect a particular a deformity in an image, or a sort of a suspicious patch or suspicious region in my image, this CAD-X, which is called computer-aided diagnosis, will actually do a sort of risk analysis of this particular region. Obviously, machine learning and deep learning plays a great role in both the techniques. Okay, in a sense, because the first technical detection is understanding a particular pattern, whether a particular pattern exists in an image or not, and we all know that machine learning and deep learning can help in that respect a great way. And then in the case of computer-aided diagnosis, it is doing a sort of classification, right? It is doing a sort of classification, which means that if we have a good number of data set, labeled by our doctor, I can train my system, I can train my network to understand the class levels in the best way. Obviously, feature extraction and pattern recognition will be the underlying phenomenon, how they are doing it, but ultimately they will be classifying, or will be doing a sort of risk prediction of this particular image samples, and that will also help the doctors in a way that will give a sort of secondary vision to the doctor, and the doctor will be supported in a way that in the many of the cases, what we know that so many of the cases we know that the doctors looks into the image and tries to find out that what is the best point, or what is the best region of this particular organ to do a biopsy. So my CAD-X gives a sort of visualization to the doctors and tell that, okay, look, that this is the very high risk zone in this particular organ, and the doctors will try to do a biopsy at that particular region. Okay, that means, and also the doctor can see and say that, okay, there is nothing much risk associated with this particular image, and then there can be a sort of other sort of therapy can be applied not going for the next level of diagnosis. So these are the very beautiful aspects of the computer aided detection and diagnosis, which they can work hand in hand, and they can produce a very good support to the doctors and to the patients in the modern era. Now I will try to move into the concept of machine learning, which we will be discussing pretty extensively in this particular lecture. And all of us know that machine learning is a fantastic way by which we make our computers intelligent without explicit programming, right? Okay, and that was actually being coined. This particular definition of machine learning was coined by Arthur Samuels, who is considered as the father of machine learning. So what it actually means is that it means that a computer program in the very classical way is being developed through some sort of logic or through some sort of algorithm, right? That works fantastic. There is no problem or no issue in that, developing the programs in that particular way. But what happens is that as the scenario changes and as the complexity changes in this particular in a more realistic domain, these algorithms or these programs, which are classical, not machine learning approaches, they fail to deliver because some of the things which has changed in the new data which is being supplied was not being considered or not being viewed upon when the algorithm was developed. So what happens is that your system becomes a static system, and there is no point on also to push something to the algorithm, and so algorithm can just starts working better because the algorithm was not made in that form. So the only way out is that you try to develop a new algorithm based on your new stuff. So the alternative path is the machine learning, where you don't need to build algorithm based on your own logic. What you try to look into the data which is existing in the domain, right? And that data has already being analyzed in some way with some domain experts, and try to abstract that particular knowledge from the data, and try to build machines which can learn from the data and can learn from the outcome what the data has generated in the past, and can build a logic, and this logic can very well be modified or updated, provided I give some sort of new patterns or new data and its outcome. Then this particular program will be modified, and that's what is machine learning is. And to the extent is that the machine learning is something, a machine learning model is something which becomes better and better through experience. That's same like a biological model. So we know that the objects in the living world actually can perform better if they're trained, if they're more and more experienced. So this particular phenomenon is imbibed in the machine learning systems. Okay, so how they are imbibed? They are imbibed by a process called a learning phenomenon. So through the learning phenomenon in repeated intervals, and okay, that means, and maybe the learning can be done. It can be done again and again, repeated times again and again. And by this process, the system becomes better and better, okay, in terms of its performance, right? Because at the end user's point, a system is good or bad depends on how the system is performing, and the performance of the system here is not a function of the logic or the type of or the time you used to actually develop your logic. Here the performance gets scaled up by the new data or the new experience you share with your system. More and more new experience, more and more varied experience are being abstracted by your machine model, by your machine. More and more your models get strengthened, and more your model can behave as an adaptive system, right? And that's why machine learning is such a fantastic domain of activity. Okay, I will not go into details of the different type of strategies of machine learning, but just as the figure tells you, the machine learning strategies are broadly classified into supervised, unsupervised, and reinforcement learning. In the case of supervised learning, we use a sort of already existing knowledge in the domain, which is called the training data, and using the levels of the training data, we try to build a model, and the model works pretty well if we have a large amount of training data, and if we have actually abstracted the correct model. In the case of unsupervised learning, the way it works, it tries to get the knowledge by identifying the particular the differences or discrepancies in the data, okay, and tries to group the data, which are more similar in terms of a metric, or they are far apart. Okay, that means if their distance in terms of a metric is higher than a threshold. Okay, and this way, what we try to do, we try to associate data with each other, or we try to disassociate data with each other. In that process, we try to form different types of independent groups, and these groups are called clusters, and that's the way we try to ultimately find that which data belongs to which group, or which data doesn't belong to which group. Third one is the reinforcement learning. The case of reinforcement learning mainly came when we try to challenge the existing knowledge which is already in the domain. So can my machine develop its own knowledge building strategy? Can a machine can develop a sort of learning by itself? Okay, and that's the way it works. It is a sort of iterative process of exploring the data, and it tries to work out. Okay, yeah. So yeah. So is it changing now, Omar? Is it changing? Slides?
Yeah.
Okay, good. So now I will go to something on the history of the machine learning in the context of medical image processing. As we know that the primitive medical image processing applications or the algorithms worked on the very low level features, which are pixel level features, right? At that point of time, we were using some sort of naive computational functions to compute a distribution which is only defined at the pixel level. Next we scale up. Where we try to work on some on the learning techniques, which are basically supervised learning techniques, like we have in SVM, support vector machines, and naive-based type of architectures, where we try to learn the features and try to train our model. Next technique, or the next step ahead, or the present era of machine learning is the deep learning, which is working predominantly in this present decade. And what it tells us is that it is not required.
I guess we are facing with some network problems, so we are waiting for Professor to continue the speech.
Mm-hmm. We hope the Professor Amlan to connect again, and now we are waiting for him. Yes.
We are still waiting the professor. At the end of the session, you can ask your questions about recent techniques on deep learning to our professor. I guess there is a low band network problems on his computer, so we are still waiting for him.
Professor, you have a connection problem. We hope the Professor Amlan to connect again. You call him and he will check again.
Welcome back, Professor.
Okay, fantastic. Yeah. So what I was trying to say is something like this, that that when we try to detect the edge features in the next layer, what I try to do, I try to use the next level of extraction process feature, which can not only which can work on the detected edges and can try to apply some sort of spatial features or contour features to identify what happened. Okay, from a bit earlier. Okay. So this is fine. Okay, great. So, okay, great. So, yeah. So so this particular deep learning is something what tries to emulate the activities what goes on in a brain. And obviously it is not that we are at a level where we have emulated the entire activity, but the inspiration of deep learning is nothing but to start from a very simple function like a simple neuron, and to stack all of these neurons in a fashion which can actually give you a very complex transformations and can generate a higher abstraction of your data. You know what this abstraction means? This abstraction means that you will try to abstract the features in a staggering way. For example, that if I give you an image, okay, you can just apply edge filters, which are special filters which can be applied and which can detect the edge points by some derivative operations and some thresholding operations. And then provided I give the edge information, then the next level, I can connect the edge informations with the spatial correlation of the other edges and some of the contour features. We can explore all this at the next level, in the next feature level, and we can detect, okay, there are these are noses. And then at the next level, we can also try to find out that, okay, there are some correlation between the other objects of the images like eyes and all these things, and then we can detect that this is a face. So what it actually does, it tries to functionally evaluates the data and tries to abstract the features in multiple levels, and so that the ultimately our highest level of abstractions can be achieved. Okay, and that's what is all neural network. So that is what is a multiple layer of transformations, and it tries to imitate the multiple functional regions of our brain. Okay, and very soon we will see that our network also follows the same sort of repeated functions to the, okay, our deep network also forms a set of repeated functions to extract the information from your data. So let's try to understand it in a very naive way. Okay, so let us see that what these three patches tells us. Okay, these three patches, if we try to look at a bit carefully, these three patches represents that, okay, this particular patch has a particular affinity towards the pattern which is 111 in this direction. This particular patch has an affinity which is a 1-1 pattern in this particular form, and this particular patch is an affinity which is 1-1 form from this particular form. So now all this particular small matrices are actually can be considered as a feature extractors or feature matrix because they will amplify some features. Well, let us look into more details what I try to say. So let's look into this particular diagram. This is a particular pattern. Okay, this is a particular pattern, right? On this pattern, you see that if I try to find out the features of this pattern, I can tell that, hey, look, that this particular pattern has a good match with this particular filter here. Okay, this particular pattern has a good match with this particular filter here. Okay, and this particular pattern has a good match with this particular filter here. Why? Because this particular filter tells that this particular filter amplifies its results or gets the best result when they have a maximum overlapping of the filter weights with the data. And we see that this particular filter has a maximum overlapping with this region. Similarly, this filter. So to find out a pattern which is like X, it is not a particular. A single feature can give it to me. I can run this particular spatial feature extractors or spatial, or I can tell convolution kernels which can move over this entire image and can actually extract the features in a sense that wherever they find a feature match, they will generate a good value, right? And that's all we tell that is a filtering. So if you go next, so you see that how the filtering works. So you see that this particular matrix, okay, this particular matrix which is the feature matrix, and this particular image which is the patch in an image. That means when I convolve this particular matrix on this particular region, okay, it generates a data based on just multiplying the weights of the feature and the value what I get in that patch of the image. Okay, and if I do that, I can, if I complete the whole patch, convolving the whole patch, what I actually get, I get a set of values, right? And this set of values are good because I can have only the values -1, 0, and +1, because all the values are either -1 or +1. So combining them, I can only get the values of -1, 0, or +1. And this feature is an exact match with this particular this particular filter is an exact match with this particular patch, because you see that the value is maximized. So that's the ultimate motivation of a filter. So a filter works on a particular patch of an image, and if the filter feature and the spatial patch feature has a good matching, then that filter outcome will be maximized. Okay, and that is what entirely is the filtering in the domain of our neural networks or convolution neural networks. So if you go on, you will see that you can now move on this filter. So this filter will now move on or will sweep across the image according to the dimension of the image, and will try to generate these values of the filter of the convolution of the filter. Similarly, if you take another filter, okay, if you take another filter, you will see that okay. So this particular filter will not give very strong values corresponding to this region, because this filter is not so well mapped with this particular feature, right? And so you see that the feature value decreases 0.55 compared to the one which was a good feature value. So what I do, I actually convolve this particular filter matrix. That means over the entire image in the patch form, and we try to generate this particular data, which is the convolution output for this particular image corresponding to this particular filter. Okay, but if we look carefully, we see that this particular size of this particular convolution output and the size of the initial image matrix are a little bit different. So the initial image matrix was a bit larger than corresponding to the outcome of the convolution filter. This is because as we have moved in a stride length of 1, which means that first I covered this particular matrix, this particular patch, and then I move just write one column, and again do the same operation. So in this way, the number of results what I generate is a less than number of the elements in the initial matrix. And there is a good equation which I have just given at below, which tells that it is nothing but I minus f. I is the image size. For example, this particular example is an image size of 9 cross 9. So I can take I as a 9, and this particular filter has a size of 3 cross 3. So I can take the value of f as 3. And P is for padding. I'm not using any padding. Padding is obviously is used because as the filter sweeps across the image, at some point it will not find any image data. So to manage that padding is used. But for this example, I haven't used any padding. And the stride length, that means the interleaving hops, what this particular filter is doing. For the current example, as it is just shifting one position in the right in each filter operations, I have taken s or stride length equals to 1. Okay, that means, and if you equate this particular value of c corresponding to this particular example, you will get a value of c equals to 7. So the convolution output matrix will be a 7 cross 7 matrix. Now this is for one particular feature. Now this is actually done for multiple features which we have initially shown. So this particular feature, okay, that I have shown the example. okay, working with this particular feature, but you can work with this feature and this feature. So you can have a number of feature kernels, and each of them will work on your data independently, right? Independently, and will generate their convolution output. So this is the rate from my convolution kernels. So these are convolution kernels, and these convolution kernels will work on this particular data. And if you look into this particular kernel, you will see that each of the kernel has a particular pattern of the data. You see this particular kernel gives a good value in these two regions, and this particular kernel gives a good value in these two regions. Similarly, this particular kernel gives a very good value in this region, and this particular kernel gives a very good value in this region. So it means that I can easily understand that what is my spatial location of my feature corresponding to each of these filters. So if I tell this is a filter A, this is a filter B, this is a filter C, so filter A gets a maximum outcome at this point, filter B gives a maximum outcome at this point, filter C gets a maximum output at this and this point. So it means that these regions of the images are perfectly matched with the features which these filters define. Okay, and that's what is filtering. Okay, because in the filtering, what we try to do, we try to extract the information which are as per our filter specification, and we get a very low value for which the filter specification is okay, that, yeah, so it's just the inverse. So filter maximizes some value and doesn't give good response for some other set of values. And similarly is the case of the convolution filters. So now in the first layer of convolution layer, what I have discussed is that we have a particular series of convolution outcomes, right? So now these outcomes will be going to the second layer, which is called the pooling layer, which actually shrinks the image in a sense that it only tries to capture the information which actually does a representation, as a very good representation of the information of the previous convolution outcome. And in this process, it reduces the size of the information also. So that means, and also there is another thing we need to take care is that once you understand the pooling, I will get to that. So if you look at the pooling, so pooling works on a window, okay, and within this window, it tries to take the maximum value, okay. So in this window, you see that one is the maximum value. So instead of all these values, I can just tell that, hey, look into this particular region, and I know that there is a good feature outcome in this particular region because at least one value has a 1. So it is sufficient for me to record that in this particular region I have a good feature outcome, and okay, that means, and hence for this I store the value 1, or the maximum value of the outcome of the convolution filter. And in this way we go on doing this, okay, and we go on doing this and what I have done, I have obviously generated a very good representation of this particular information in the pooling layer, because it restores the values which are strong very well, because it is always taking the maximum value or the maximum impact of a particular region, okay, so that it can be fed to the next layer. And in the other process also, what it does, it also does a little bit adjustment in the terms of the exact spatial location of the information. So see that in this particular window, in this particular window, though I have taken 1, but if the 1 was somewhere here, or 1 was somewhere here, or 1 was somewhere here, still there wouldn't have been any change in the pooling outcome. So what it does, pooling outcome tries to give a sort of invariance in respect to some small local shift in the image information, and that works wonderfully. So similarly, like the convolution outcome, we have the outcome for each independent filters. Similarly, we have the pooling outcome of each independent filters. Okay, and last but not the least, what I now need to do, I need to now pump out those particular values which actually really contribute and those values which don't really contribute. And this is called the activation layer of your network. And in this activation layer, what we normally use or default use is a function which is a ReLU. And okay, and this figure which seems to be a switch. This is actually the ReLU function. So what this ReLU function does, this ReLU function actually suppresses all the values which are lower than 0, which means that this function is actually is a max between your x and 0. So if a value is below 0, then always if you pick, okay, it will put 0. If a value is above 0, then we put that particular value. So if you span our pulling outcome, you see that using the ReLU, what I have done, I have mostly represented the data which strongly represents my feature outcome. Okay, and those values which doesn't represent my feature outcome well, those values doesn't go to the next layer, and those are all normalized to 0. So this is a sort of normalization. This is a sort of giving a prominence to the values which are which will help you to classify or generate an effective outcome in the subsequent stages. So with this, you can now make a stack up of this, and you can make a convolution, ReLU, and pooling, and you can make a first layer of your network. But again, as I told, that these filters may be the first level of filters what you are applying, maybe the H filters. After you do the H filters, what you need to do, you need to find the data which is generated or the outcome which is generated by the H filters. Can we work on those outcomes, and we can further extract a sort of feature from those outcomes, maybe the connected edges, and then we can do the contours. And once the contours are done, we can go to the shape level features, and we can find that, hey, whether there is a eye, or there is a nose, or there is something in the information. And then we can again go with a much enhanced type of correlation between the patterns detected in a spatial domain, and whether we can detect that, whether we can tell that, okay, look, this is a face. So you know that this particular stages of convolution, pooling, and ReLU will go in a sequence, and ultimately it will generate a sort of values which are very well compressed, and which is sufficient to determine or to generate an outcome which I want to have. So the last stage, which is called a fully connected layer, or a flattened layer. In the flattened layer, what I try to do, I try to expand all these values in a single layer, in a single vector, and that's the way I generate. Now what I do, I try to associate labels with these particular vectors. So you see a particular vector which has 1 here, 1 here, 1 here, 1 here, and 1 here will be associated with a label X. Okay, and similarly, a vector which has a 1 here, 1 here, 1 here, and 1 here, associated with a value O, because based on my feature extraction, based on the training data I supplied for the X and O, these are the outcomes, which means that these outcomes actually based on the feature values which have generated different values at different locations of this particular vector, and the pattern of the values actually identifies a particular label or the other, right? And this might not be so easy always. Okay, you might not generate this particular score of a particular level in terms of your outcome at one particular stage. So you may require multiple stage in a fully connected network also, right? And that actually builds up the entire tree of convolution network. right? And then I've tried to explain you that the basic network, how it works, because the entire medical image analysis and processing mostly based on the variants of this particular type of network. Okay, so I can take, that means I will take the questions at the end. So if you have any questions, please let's keep it with you. Okay, that means I hope that there will be some questions coming, but let me complete the entire tutorial, and then I will come to answer all your questions. Okay, so what we learned here is that obviously the learning process actually settles down the features in the convolution layers. Okay, and the stages what we try to do, and then obviously we also have to learn the weights. Okay, from your outcome of the convolution layer to the so that they can give a very good decision at the outcome of the fully connected layer. So this requires obviously a training data, right? What that means to generate the outcomes of the convolution filters, you need to pass a lot amount of data so that all the features are well learned and the convolution kernels are well explored to maximize the features, to maximize some features, right? And once the features gets maximized, then I pass it to a standard network, which is a fully connected network, which actually works as a pretty standard neural network model to classify the outcome which has been generated by the convolution layers, right? And that's why deep networks are called as a feature extraction and classification goes in a seamless way. Okay, that means you don't have to interrupt the system in some way that, hey, first I do feature extraction, first I learn the feature as step one, and then I push the feature to the classifier to classify it well, which is the traditional machine learning. Okay, and that's the way the deep learning works very efficiently. But again, said that, okay, that so you have to remember that as the features are learned automatically, you have to supply your network enough amount of information so that all possible features are well learned by the network. So putting it all together, this is the picture. This is the picture. What it shows, and this shows that what I'm trying to do. So the entire medical image will be decomposed into some patches, and the convolution kernels will be trying to extract the features based on the filter what I'm applying, and there can be a series of convolution filters of extracting different types of features, and the features outcomes are slowly and steadily being massaged with the pooling layer and the next layers of convolution layers, and ultimately we have a sort of a vectorized feature map. And this vectorized feature map is very good to run through your fully connected network and can give you a good score in terms of your outcome. So if we look into the parameters which are there in your network itself, which are called the hyperparameters or the knobs, you need to know or adjust a number of features in the convolution layer. Or what a number of features means that if you go through a network, number of features means that number of convolution filters you are using, the size of the filters, or that whether you want to concentrate it more spatially, or you want to concentrate it on more globally. Based on that, you define the feature sizes, and then you go with the window size, window stride. For the case of pooling layer, if you are going with a larger window stride, you are trying to search the feature outcomes at a little bit larger distance. If you're working with a smaller window size, you mean that you are trying to search the feature outcome in a smaller neighborhood, in a smaller locality. And then the fully connected network actually gives you, that means how you're defining a classifier. So if you are using the CAD in this particular way, using the deep networks, I think, and that's the way how we're trying to do the XVA. That means without the effort of explicit elaboration of features, these networks can very well trap the features and use the features in the classifiers for detection or for diagnosis. So if we look into the medical imaging tasks, there are a plethora of tasks. Obviously, classification, as I already discussed, and diagnosis process, detection, I discussed in the detection process. Obviously, classification and detection works fine, but the most fundamental is that we need to do the segmentation to separate out our region of interest from the rest of the image information. And last but not the least, we require to have a good visualization, because the users of this outcome is not the computer engineers or the machine learning guys. It is mostly the doctors, the radiologists, or maybe the patients, or maybe some other agencies. So you need to have a good visualization so that the doctors can help to reduce their time, and it can help to give them a good inference based on the analysis what has been done. So obviously, some of the things we need to take care, as we know that the data collection is one of the issue. Model selection, the data collection means that is the most predominant issue in the case of medical image, because we know that to get the data from a medical house, it requires time. To get the label data from a medical house, it requires much more time, not only for the researchers, but for the UNIPED to have the time from the doctors who will label the data, right? And it's very difficult to get the time of the doctors who are the busiest person in the different in the scenarios. And suppose consider the present scenario of pandemic. Okay, it's very difficult to get the label data of the pandemic information, also of the COVID information, also from the doctors. So how we handle those scenarios, how we can work with a smaller amount of data, and still we can give an appreciable amount of results. Okay, next is the model selection. There are a plethora of models. Okay, plethora of nets. I will discuss some of them in this lecture. But what is the best I have to take care, right? And obviously, as I told, result interpretation and visualization is also much of importance. So one thing is very well known, which is called data augmentation, and data augmentation works pretty well in the case of medical image analysis. So data augmentation works with some sort of statistical variations we introduce in the data in a very systematic way, so that we can generate a large amount of variations between the images, and in the process we can generate a good amount of training set. Other process is called a transfer learning, where what we try to do, if we don't have a larger training set to train our network, what I do, I train my network with an available data set from another domain. It's maybe I'm trying to detect a chest patch, but I don't have a sufficient amount of data. Can I use some of the databases which are already existing in a medical image domain? Okay, maybe chest X-rays, but not for my tuberculosis patch, but from other sorts of disease, and there is a good amount of data available. So let's actually make our network learn with the basic features what a chest X-ray has. Okay, and then fine tune the network with a small amount of label data, which for the specific case of tuberculosis of the chest X-ray I have. Okay, that is the process is called. That means first develop the network and try to train the network with the most commonly available features, and then try to put your training data set and try to fine tune your network in terms of the specialized features which your data set has, though the data set is very small. So that's called the scenario of transfer learning. Now I quickly browse through some of the very important networks, okay, which are available in this particular domain. Right, the most common network is the UNet. Okay, and it is a variation it is a variation of the CNN, what I already explained you. UNet was one of the winner of the challenges in computer-aided detection in 2015. It was proposed by Ronenberger, a German researcher, and that is the most widely used network. What it does, it actually tries to this particular structure is a U structure, and okay, that means, and if you see this particular process, you will see that the data gets contracted in the first half of the U, and data get expanded in the second half of the U. Okay, and also there is a line between this to this, which means that this particular network uses the outcome of this particular layer. This particular layer uses the outcome of this particular layer. Actually, the last convolution outcome is being fed as an input to this particular layer, and similarly all the intermediate layers. And this way, it tries to actually correlate with some observations which are being done in a contracted path, and then it tries to use that information to again extrapolate the data and try to generate in a form, and that's the way how they have been pretty heavily used in the segmentation of the images. There is something called generative adversarial network, or GAN, and this is also pretty heavily used. Generative adversarial network is actually used to find the finer features in the image. The concept here is that you can always generate a sort of fake what I can say, a fake feature set, okay, which is fake in the sense that it is very close, but it is not exact. Okay, and try to find that how this fake feature set and the actual feature set actually gets differentiated. What is the distinguishing parameter? Because this distinguishing parameter is the most difficult discriminating parameter, which is a handle for you to identify this particular pattern in the image in a very specific way, right? And that is the way how the generative adversarial network works. And this has been tested with multiple examples in the case of the brain lesions or brain patches. This is a very new work which has been done in 2018, and this is a different in a way that this actually works with multi-scale images okay, in the form. So what it does, and it uses multiple pathway instead of a single pathway which is normally followed in the UNet. It works in a multiple pathway. So if you look into this particular architecture or this particular network structure, you can see that each of them actually takes all these four inputs, and these four inputs are actually different modalities. One is T1, one is T2, one is T3, and one is I think the water absorption. Okay, yeah. So image okay, and secondly, this is a multi-scale, and then secondly, that means it works with different resolutions of the multi-scale images. So it works on low resolution features as well as high resolution features of the same image, okay, and tries to extract the patterns from the low resolution as well as the high resolution and mid-level resolution of the image, and then tries to merge these patterns, okay, and it tries to merge this pattern. So what happens? It tries to inspect, okay, it tries to inspect the images very thoroughly and in a multi scale way, so that if we try to do the analysis in the uniform scale, maybe the higher scale information gets normalized, or the lower scale information gets normalized. If we do the analysis, or if you extract the patterns in multiple scale, what it does, it actually prioritizes the features in all the scales, and then it supplies to the network, and that is very good for the vertebra, because each of the vertebra has different responses in terms of the scales and in terms of the resolution response in terms of the structure of the vertebra. So vertebra, so a variation in a vertebra is huge. Okay, and this type of network helps us to learn or to extract the features in a very efficient way. This is one of the work which is done by one of my student Pabitro, and this is a good work in the sense that all of us know that MICAI is a pretty good conference where they throw the challenges, and okay, and this particular work, what it did is basically there is something called the Gleason score of the histopathology image. The histopathology image is nothing but the biopsy image of the tissue of the prostate, and this particular Gleason scale is a sort of classification of the malignancy. So higher and higher Gleason scale, higher and higher Gleason rating of particular region, it means that it is of a higher grade of cancer or higher risk of cancer. So the problem was that we had a less amount of data, okay, to do that, and the process we followed is nothing but a sort of transfer learning. So we did a transfer learning, and we used some technique like convolution encoder decoder. I'm not explicitly discussing this due to shortage of time. You know that the convolution encoder actually tries to minimize the feature space in a better way, and okay, that means, and thus tries to reduce the time in the process of the training. So reduces the training time. So by using the transfer learning and convolution encoder decoder, Pabitro was very good in getting a very good result, and this particular result has been listed in the MICAI top contributions in 2019. So that is one of the results which has been done by one of my students, and then last but not the least, this is a very beautiful network which is now predominantly studied, and a lot of research are going on this network, which is the COVID net, which is being designed by the group from Waterloo University, and this is also a convolution network in a sense, but it uses a special type of convolution network, which actually uses some sort of interconnections between the stages, some sort of long interconnection between the stages, and some sort of a different set of convolution filter, different variable sizes of convolution filters to explode the image in a different way compared to the normal convolution network. And another important thing is that this is a little bit lightweight type of network compared to the existing, or compared to the standard networks, right? So they were pretty good in finding the patches of chest X-rays, and they have also uploaded their entire work in the GitHub, right? So what I mean to say at the end of my lecture is that obviously deep learning in medical images is showing a very promising results, and it is something we can coin as data-driven therapy, or data-driven data-driven diagnostics. Okay, and obviously it is actually a lot of the challenges it has overcome as we are doing data-driven, as we are learning from the learning lessons from experience, and as the scenario of disease diagnosis evolving, we can always adapt to the evolving scenario if we have systems which are like deep networks. And obviously the accuracy, sensitivity, the potential accuracy of this type of techniques are actually leading towards implementable mechanisms and new products which can serve the society in the very best way. So last but not the least, I just want to let all of you about my group. I think some of my students are also there in a 2 days lecture. My students are working on different modalities and different structures and organs of the body. Like that, we are working with the lung nodules in one of my student Jilam, we are working also with digital X-rays, and we are trying to find the bone deformities. With Raka is working on that. Pubali is working on the brain segmentation. Pavitra, I've already spoken about him. Pavitra is working on the segmentation of the vertebra in the 3D domain, and Shomabuli is working on 3D reconstruction and visualization. So this is the group where I started from 2014, and some of the students will be graduating soon. And I hope that this group will be a growing group in my research domain. And I invite so all of you to get connected with us and let us know that if you have any research ideas. So thank you, and I am open to questions now.
So we have some questions about Tier.
Yeah, perfect.
Mentioned in the question and answer section. So the first one is coming from the Yasmin. She's asking about can we use multiple filters that have high correlation with particular image feature?
Yeah. So that's that's actually technique. So normally when we look into the image, okay, that means you know that what are the features we normally need to extract. So in the fundamental level, that means all these networks tries to extract the features which are pretty straightforward. Okay, like some of the spatial features, some of the texture features. Okay, like this. The difference happens when we go up in the higher in the order, because when we go in the higher in the order, we are more towards the classifier. So the fine tuning of your network in terms of the features are mostly required in the higher layer of your networks, and there are a lot of strategies by which you can actually try to find out which are the convolution kernels which are best. And actually one of the way is the GAN, as I already discussed, and another way is also transfer learning, by which you can know that what are the features you need to only fine tune, because it was all the features you need not to fine tune for a specific activity. So that's so that's obviously you need to work out if you want to do a very custom type of network. But normally the networks that is available, that means can be actually the UNet, if you tell, it's pretty well works for most of the biomedical image analysis, but again it can be a overwork. It might do overwork or underwork in some of the cases, and in those of the cases you have to look into the higher convolution filters at first, without hampering the lower convolution filters. Yeah, that's my answer. Yeah.
Okay, thank you. There is another question coming from Yasmin again. She asks that can CNN classify effectively pictures of one independent variable?
Pictures of one independent. What's that?
Yes, exactly.
That? Okay, can you repeat that again once more? That means so CNN. Okay, when it is in one independent variable in a picture. Okay, so one independent variable means that you are trying to say there is only one feature in the image, or what you are trying to mean? I need to understand the question a bit better. That means if you have only one feature, okay, that means obviously nobody will use this type of networks. Yeah, that's pretty sure. Yeah, you can go with simplistic like SVM or this type of things. But this type of networks are pretty well when you have lot of features to handle with. That means and you know the number of parameters it goes up. Okay, in the network. Okay, in a standard network. So you have if you have those many parameters in a network, then only this type of technique works good. That's a pretty costly technique, right? Yeah.
Yeah. Another questions about history of the health. What I mean is that can we use the previous health records to our model to learn the next diseases?
Okay, so you want to know whether the heart, I mean the signals which are captured from the heart are fine to track the diseases. Yeah, this is a pretty good work, good work going on, because doctors say that the heart and lung sounds, that means heart and lung sounds are the most predominant disease signatures, right? And we know that our old doctors, when all this type of radiology and all this imagery was not there, they used to only use a stethoscope and used to tell that, okay, you have this type of problem. So provided we can detect it accurately and clearly, I think it is a good way. Actually one of my student actually started a new research in this domain, where we are trying to detect the heart and lung sound using some sort of wearable device, and trying to build a classifier which can work well with a point of care service to the particular patient. But this is pretty challenging because the noises are very, very high in that particular domain, and an experienced doctor can know that, okay, this is a particular heart sound which is good or bad. But a trained machine in that respect is a bit of challenge, but we are working on that. And a lot of research group across the world is taking it as a very good research problem. Yeah, thank you for the question. I think this is a very good research problem.
Okay, thank you again.
Yep.
Another question coming from Mukherjee. Mukherjee, sorry that. Asking that if there exists less variability in the structure of different types of an organ, will data augmentation be a good option to overcome small sample size problem?
Yeah, very pertinent question. Actually, this is one of the work what we have actually effectively done. Actually, one of my student, I don't know whether Jhilam is here or not. Yeah, I think she is here. Jhilam Mukherjee, she would be graduating student from my group. So what she had worked out is that means we had this problem. We are working with the detection of lung nodules, right? And actually if you go to a medical doctor, or if you try to take a suggestion of a medical person, they will always tell that you should work on real data. And obviously the structures are small, right? If the structures are very, very varied, right? It's a difficult proposition, because whether we can statistically actually generate those variations, because those variations are pretty abrupt if the structures are pretty different. So then what we try to do, we try to generate some sort of techniques like undersampling in those particular results which are pretty available, and try to do oversampling on the results which are less available. Okay, and try to make a balance in our training data. But the question is that this is one of the problems where we have the data, but in the data the classes are just not equal. One class is represented by 20% of the data, and another class is represented by 80% of the data. Then we can use a sort of different type of sampling. But that also fails if itself we have a very small amount of data. So itself we have a very small amount of data. If you don't want to use this type of techniques like data augmentation, I think another technique you can try, which is called transfer learning, right? And that might help you in that case.
Okay. Yeah. Thank you very much. And as a last question, I would like to ask to you, what are your expectation on next or future advances in machine learning or in deep learning, especially?
Oh, that's a very good question. Actually, yeah, the advances I am seeing that every day. That means if you look into the paper of in the COVID pandemic scenario, you will see the highest hits of the paper are basically on the COVID-19, COVID-19 data set and the COVID-19 this X-ray paper. So that obviously tells you that how much that means how much type of faith the researchers have in the deep networks at the present. And also it is being well supported by the ecosystem, which tells that you can now do cloud computing, you can have GPUs either in your own laboratory, or you can take the GPUs from your cloud resources. So the entire ecosystem, not only because algorithm and the concept existed maybe 20 years ago. The flurry of deep learning is because the data is availability of data, and next the availability of resources, which are gradually pushing us towards deep learning. And I think that this is not only in computer-aided diagnostics, but in many applications of video, image, pattern recognition, and text analytics. This will be more and more explored. Okay, and there is a fantastic career options or a fantastic path of research. That means now those of my PhD students who will be just graduating, I am just pushing this towards deep learning, and those who are joining, I'm just saying, hey, you have to know machine learning, because unless you know machine learning, unless you know perceptual network, there is no point in moving towards deep learning. But provided we know machine learning, you have some hands-on in machine learning, you should go towards deep learning and try to explore that, because that's really flourishing.
I see. I guess there is no more questions. So
Okay.
Thank you.
Okay. Thank you.
We will thank you for Professor Chakrabarti for him today's live session. We are thankful for him. This was IEEE Connecting UX Talk, cooperating with IEEE Young Profession Turkey and Region 8. And we also thank for all participants for joining us. Thank you very much.